Please subscribe to support the channel. How do you fly through every galaxy when you can't even see the whole universe? That's the first hard limit. This trip has a boundary, and it's not a choice, it's set by physics. So what's the size limit? We can only work with the observable universe, the region whose light has had time to reach us since the Big Bang. In co-moving distance, its diameter is about 93 billion light-years. Co-moving just means we describe positions using a coordinate grid that expands with space, so we can compare locations without having the ruler itself change length over time. It's the distance between us and a distant region now in that expanding map, not the distance the light traveled along its path. Anything beyond that boundary is currently unobservable, no matter how good the telescope is, because the light has not had time to arrive. Now here's the part that sounds wrong at first. The universe is about 13.8 billion years old, but the observable universe is much larger than 13.8 billion light-years across. How can both be true? Because space expanded while the light was traveling. The photon always moved locally at light speed, but the amount of space between the source and us increased during the trip. So the look-back time to the earliest light is about the age of the universe, while the present-day separation to the regions that emitted that light can be tens of billions of light-years away. This is why age in years and size in light-years don't match the simple way your brain wants them to. Alright, boundary set. Next question, how many galaxies are we actually trying to cover? If you've heard hundreds of billions, that was a standard headline for years. It came from wide surveys that counted detectable galaxies across huge areas of sky and then scaled up. But deeper observations changed the situation. When astronomers stare longer and push detection limits lower, the number of faint galaxies rises fast because small galaxies are far more common than big ones. Some analyses argue totals closer to trillions once you account for faint, small galaxies that older surveys could not detect. So what number do we say for this mission? The honest version, older estimates were hundreds of billions, and newer work that corrects for faint galaxies argues trillions. And you also say something viewers don't hear enough. It's not a single exact count. It's a range with uncertainty. The reason is simple. The answer depends on what your instruments detect and how accurately you correct for what they miss. Which leads to the next question that decides the whole story. What counts as a galaxy in the first place? Telescopes don't label objects. Data pipelines do, using rules. One rule is a detection threshold. The signal has to rise above background noise. Another is surface brightness, how spread out the light is on the sky. A very diffuse galaxy can be harder to detect than a compact one with the same total light because its glow blends into the background. So a real galaxy can be present and still fail the survey's detection rules. Then there's a practical problem: overlap. In deep images, galaxies crowd together. The software has to de-blend them, meaning separate overlapping light into multiple sources. If it oversplits, one galaxy becomes two entries. If it undersplits, two galaxies become one entry. This changes number counts, and it can bias what the typical galaxy looks like in your catalog. And galaxy can include extremely small dwarf galaxies. Some dwarfs have very low star counts and very low luminosity, but they're still gravitationally bound systems with their own evolution. Near us, we can sometimes identify dwarfs by resolving individual stars and measuring motions. Far away, we can't resolve stars, so the same kind of object might fall below the surface brightness limit and disappear. Different surveys use different thresholds, so two catalogs can disagree and both can be defensible. So here's the unavoidable trick. We cannot visit galaxies one by one. If the true count is hundreds of billions or trillions, a stop-by-stop route is impossible. The only honest version is sampling. We fly through every galaxy by taking representative slices of the universe and scaling up from what we detect. How do we do that without guessing? Two approaches work together. Deep fields stare at a tiny patch of sky for a very long time to reach extreme faintness, so they reveal the small and distant galaxies that dominate the population. Wide surveys scan large areas to capture the big structure, the nearby universe, and rare bright objects. Then we combine them using statistical inference. A key tool is the luminosity function, a measured distribution of how many galaxies exist at each brightness. Another key tool is the completeness function. For a given brightness, size, and surface brightness, what fraction of galaxies the survey actually detects. Put those together and you estimate the unseen population instead of pretending it doesn't exist, and you attach error bars because real data is noisy. Now for the part that turns the route into a timeline. When you look farther, you are also looking earlier. Light takes time to travel. A galaxy a few million light years away is seen a few million years in the past. Nearby clusters are tens of millions of years back. At very high redshift, you're looking more than 10 billion years into the past, toward the era when galaxies were smaller, more irregular, and still assembling. This is why a distance map is automatically a history map. You never see the far universe as it is right now, only as it was when the light left. So the mission scale is set. The boundary is the observable universe, about 93 billion light-years in co-moving distance. The target count is at least hundreds of billions and possibly trillions. The count depends on detection thresholds, surface brightness limits, and deblending. The method is sampling plus statistics, not a literal checklist, and the route is also a timeline. Now the tension goes up. If photons are the only thing carrying information across that distance, how do we build a galaxy map when dust, faintness, and redshift are actively hiding the targets? If you can't physically stop at trillions of galaxies, then what if the engine of this mission? It's photons. Every galaxy we fly through is reached only because its light reaches us. That light is weak, it gets stretched by expansion, and it gets buried under background light from the solar system and the Milky Way. So the job is not go there, the job is detect the light, measure it, and prove it came from a galaxy. So how do you collect galaxies in the first place? Deep fields. The method is simple and ruthless. Pick a tiny patch of sky that looks empty and stare at it for a long time. The Hubble Ultra Deep Field did exactly that. In a patch only a few arc minutes across, Hubble detected around 10,000 galaxies. That matters because it gives you a controlled sample where you can push to extreme faint limits. You can count how many galaxies you detect at each brightness, and you can see how quickly the number of detected galaxies rises as you push deeper. That tells you something uncomfortable. Most galaxies are not big, bright spirals like the Milky Way. Most are small and faint, and you miss them unless you go deep. Deep fields also expose a second issue. Because the area is tiny, you can get cosmic variance, meaning you might land on a region that's slightly overdense or underdense compared to average. So deep fields give you the faint end, but they don't give you the full map. That's why deep is not enough by itself, and that's why the counting has to be combined with wide surveys later. But here's the next problem that raises the stakes. What if many galaxies don't show up well in the kind of light you're using? This is why infrared changed the whole game. Two effects push you into infrared. First, dust. Dust inside galaxies absorbs visible and ultraviolet light. A galaxy can be forming stars rapidly and still look unimpressive in visible images because dust blocks the bright young stars. The absorbed energy doesn't vanish, dust re-radiates it at longer wavelengths, so infrared and sub-millimeter become essential if you want the full star formation picture. Second, redshift. The farther a galaxy is, the more the universe's expansion stretches its light to longer wavelengths by the time it reaches us. A galaxy that originally emitted a lot of its light in ultraviolet and visible can show up mainly in infrared when it's very far away. That's why JWST, which is built for infrared, can see early galaxies at the same depth where Hubble could only see a fraction of what was there. It's not that Hubble was wrong, it was looking in the band where the signal is no longer concentrated. Now ask the practical question. Even with infrared, how do you know what you're actually looking at? You don't rely on one wavelength, you use multi-wavelength data because different wavelengths trace different physical processes. Optical and infrared mostly trace starlight, and infrared sees through dust better. Ultraviolet is useful for identifying very young hot stars, so it tracks recent star formation, but it is also easy for dust to hide. Radio observations can trace neutral hydrogen through the 21-centimeter line, which tells you where the raw gas reservoir is. Sub-millimeter observations trace coal dust, which often tags hidden star formation, and dense gas regions. X-rays trace very hot gas and also reveal accreting black holes, because gas falling into a supermassive black hole produces high-energy emission. Put this together and you're not just finding a blob, you're measuring what the galaxy is doing, forming stars, holding gas, heating gas, hiding behind dust, or powering an active nucleus. So what does your map actually look like when you're done? It's not a wall of images. The real map is catalogs. Survey pipelines take the images, subtract backgrounds, identify sources, separate overlapping sources as best they can, and measure fluxes in different filters. Then they estimate shapes and sizes, because size and shape affect detectability. They attach uncertainties to everything, because faint sources are noisy. And the catalog becomes the working universe. Each row is one object, and each column is a measured property. This is also where distance estimates come in. If you have spectroscopy, you measure specific emission or absorption lines, and the redshift is precise because you're matching known atomic features to where they appear in the spectrum. If you don't have spectra, you estimate photometric redshifts from colors across many filters. That's cheaper and faster, but it's less exact, and it has failure modes, like dust making a nearby galaxy look like a distant one or vice versa. Catalogs also store quality control information, flags for blending, warnings about nearby bright stars, notes about possible artifacts. Those details sound boring, but they decide how many galaxies you can trust in a statistical count. And here's the tension you can't dodge. What does missing galaxies actually mean in observational terms? It means the universe contains galaxies that our surveys struggle to detect reliably, even when they're real and common. Low surface brightness dwarfs can be nearby and still fade into the sky background because their light is spread thin over a large area. Dust and shrouded galaxies can be faint in optical even when they're forming stars intensely, so you only catch them in infrared or sub-millimeter surveys. And at higher redshift, galaxies can be so faint that even deep fields struggle, and sometimes you need gravitational lensing or extremely long exposures to detect them at all. This is why surveys publish completeness curves. They estimate as a function of brightness, size, and surface brightness how often their pipeline would detect the galaxy if it were there. Missing galaxies is not a mystery word, it's a measurement problem with known failure modes, and the best surveys admit that by stating, in numbers, exactly which galaxies they are likely to miss. So photons are the only way we reach these galaxies, and photons are this easy to lose or misread. The next question is unavoidable. How do you navigate with a signal that gets stretched, dimmed, and sometimes confused? Because the moment you turn light into a route, you have to talk about redshift and distance, and that's where mistakes happen fast. If you're navigating the universe using light, how do you tell the difference between far away and long ago? You can't use a normal distance sign. You use redshift, written as Z, and it's the basic route marker for anything beyond our local neighborhood. So what is redshift in plain terms? Light has a wavelength, the spacing between peaks. When a galaxy is distant, the expansion of space stretches that wavelength on the way to us. You measure the wavelength you receive and compare it to the wavelength the same atom emits in a laboratory. The fractional shift is Z. Bigger shift means bigger Z, and Z connects to distance only through a cosmological model, measured numbers that describe the expansion rate today and how the expansion has changed through cosmic time. In normal language, the model includes the current expansion rate and how much matter and dark energy the universe contains. Those numbers aren't opinions, they're pinned down by multiple datasets, like the cosmic microwave background, galaxy clustering, and supernova distance measurements. When you pick a standard model, Z turns into a distance estimate and the look-back time estimate. Now, here's a fast way to get lost. When you say distance, which distance are you talking about? In an expanding universe, it isn't one thing. So which distances must you keep separate if you want the map to make sense? First is light travel distance, meaning the distance implied by how long the photons were in transit. It lines up with look-back time, how long ago the light left. Second is proper distance now, meaning the separation today if you could freeze cosmic expansion at this moment and measure the gap with a ruler. For very distant galaxies, proper distance now can be much larger than light travel distance because the space in between grew during the trip. Third is comoving distance. Think of it as using coordinates that expand with the universe. You factor out the stretching so the large-scale pattern stays comparable across time. That's why papers use co-moving distance for big maps, and for the cosmic web, a cluster at high redshift and a filament nearby can be placed on the same kind of coordinate grid without constantly rescaling the ruler. So redshift is your marker, and there are multiple distances you can attach to it. Next question, how do you measure Z for real galaxies in bulk without spending hours of telescope time on every single one? Spectroscopy is the precise method. You spread a galaxy's light into a spectrum and look for identifiable features, emission lines from glowing gas, absorption lines from stars, and sharp breaks where the physics changes sharply. You match a known feature and measure how far it shifted, and Z comes out cleanly. When you have multiple lines that agree, it's very robust. Spectroscopic redshifts are the gold standard, especially for confirming extreme distances, because the measurement is tied to specific atomic features, rather than a general color trend. The cost is that spectroscopy is slower and needs more photons per object, so you can't do it for every faint galaxy in huge surveys. So how do surveys handle millions of galaxies then? Photometric redshifts. You take images through many filters and measure brightness in each band. That gives a color pattern. As redshift increases, key features in a galaxy spectrum slide through the filter set, changing that pattern in a predictable way. From that, you estimate Z. This is how wide surveys build 3D maps at scale. The trade-off is precision. Photometric redshifts are fuzzier and can be biased, especially for dusty galaxies or unusual spectral shapes. That's why surveys use spectroscopic samples as ground truth to train and calibrate photometric redshifts, and they always report uncertainty ranges. So what does Z mean in time in a way your brain can actually hold onto? You need anchors, otherwise deep time becomes a blur and you stop noticing how extreme the jump is. Start close. The local group is on the scale of a few million light years, so you're seeing those galaxies a few million years in the past. That's basically recent. Step out to the Virgo Cluster, roughly 50 to 60 million light years away, and you're looking back tens of millions of years, still recent compared to the universe's age. Push to galaxies with look-back times above 10 billion years, and you're seeing the universe when many galaxies were smaller on average, more irregular, and still rapidly building their mass. At that point, your route is also a timeline, and every step outward is a step into earlier stages of galaxy formation. Now the uncomfortable question. If the whole route depends on Z, what can go wrong when you measure it? A lot. And the dangerous part is that mistakes can look reasonable if you don't check them. Dust is one major problem. Dust reddens light, and that can make a nearer dusty galaxy resemble the colors of a farther, higher Z galaxy in photometry. In spectroscopy, faint data can hide lines, so you might detect only one feature. If you misidentify which line it is, the redshift can be wrong by a large amount. Noise near the detection limit can create bumps that look like lines or erase real ones. Blending can mix light from two objects at different redshifts, confusing both spectra and colors. Gravitational lensing adds another twist. It can magnify distant galaxies, so you may detect objects that are unusually bright for their redshift, unless you correct for lensing and selection effects. This is why serious catalogs publish uncertainties, quality flags, and cross-checks. The honest claim is not, we know the distance. It's, we measured Z with this method. Here is the uncertainty range, and here's how we account for it when we build population statistics. So hold on to the tension. You navigate by a measurable shift, but the distance you infer depends on an expansion model, and the measurement can be biased by dust, faintness, blending, and lensing. Next, we start local, because there's exactly one galaxy you can actually fly through in true 3D from the inside, and even that one hides major parts of itself behind dust. How do you map a galaxy when you're trapped inside it? That's the Milky Way problem. It's the only galaxy we can study in true 3D, because we can measure distances to individual stars. But it's also the one galaxy where our viewpoint is the most biased, because we're sitting in the disk, looking through dust and crowding. So start with the basic structure, but keep it tied to what's measured, not what's drawn in textbooks. The Milky Way has a disk, a bulge, and halo. The disk is where most of the visible gas and young stars are. It's flattened, it has spiral structure, and it's where star formation is active. The bulge is the dense central region, with lots of older stars and a different mix of stellar orbits. The halo is the extended, more spherical component around everything, containing old stars, globular clusters, and the bulk of the galaxy's dark matter. How do we know this isn't just a guess from a pretty picture? Star counts and kinematics. We measure positions, distances, and motions of huge numbers of stars. Distances come from parallax for nearby stars, and from other distance indicators for farther ones. Motions come from proper motion across the sky, plus radial velocity toward or away from us. When you combine those, you don't just see a galaxy. You see which parts rotate together, which parts are random motion dominated, and how density changes with radius and height above the disk. That's how the disk is separated from the bulge and halo in data, not by drawing lines. Now the next question that spikes the tension. What's at the center, and how do we know? The Milky Way has a supermassive black hole, and this is one of the cleanest measured black holes we have, because we can track individual stars' orbit around it. Stars near the center move fast, on tight orbits, and their paths can be mapped over years. Those orbits tell you the mass causing the gravity, and they tell you it's extremely compact. The mass is about 4 million times the sun's mass, confined to a region so compact that normal clusters of stars can't explain it. That's the key. The measurement is not we saw a black hole directly in visible light. The measurement is we saw stars orbiting an invisible compact mass, and the only stable explanation that fits the compactness and mass is a black hole. Radio and infrared observations also track emission from the region around it, because visible light is heavily blocked by dust in the inner galaxy, so even the center forces you into non-optical wavelengths. Now go one step out from the center and hit the classic evidence problem. How do we know the Milky Way has a dark matter halo? The rotation curve. In a simple system where most of the mass is where most of the light is, you expect orbital speeds to drop as you go farther out, because less mass is inside your orbit compared to the radius. But what we measure in the Milky Way and in many spiral galaxies is that the outer rotation stays high instead of falling the way a star's only mass distribution would predict. We measure this using Doppler shifts in gas and stars. If something is moving towards you, its spectral lines shift one way. If it's moving away, it shifts the other. Map that around the disk and you get rotation speeds as a function of radius. The fact that those speeds don't drop fast implies there is additional mass extending far beyond the bright disk. That's the dark matter halo. And this isn't just Milky Way special. When you look at similar spirals, you see the same basic pattern. Different galaxies have different details, but the need for extra mass in the outskirts is a repeated observation. Now ask the next practical question. Where are new stars being made in our galaxy right now, and how do we measure it? Star formation happens in dense molecular clouds. The main molecule is H2, molecular hydrogen, but H2 is hard to observe directly in the cold conditions of typical clouds. So astronomers trace it using CO emission lines, because CO is easier to detect and correlates with H2 presence. Regions where massive new stars are forming create H2 regions, zones of ionized hydrogen, because hot young stars emit ultraviolet light that strips electrons from hydrogen atoms. Those regions glow in specific emission lines and radio wavelengths. Then you have feedback, supernova remnants, stellar winds, and radiation pressure that inject energy back into the gas. You can observe supernova remnants in radio, optical, and X-rays depending on the conditions. This is not a vague "stars are born from gas" statement. It's a set of observable tracers, CO for molecular clouds, emission from ionized regions for young massive stars, and remnant shocks for how star formation affects its environment. Now for the reality check that keeps the whole mission honest. What can't we see well from inside? A lot. Dust lanes in the Milky Way block optical light, especially along the plane of the disk where most of the action is. In visible wavelengths, the inner galaxy is heavily obscured. That's why infrared and radio are not optional even for our own home galaxy. Infrared penetrates dust much better, so it reveals stars and structure that optical misses. Radio goes even further. It can map gas across the galaxy, including neutral hydrogen and molecular tracers, without being blocked by dust. This matters because if we can't build a complete picture of our own galaxy in one wavelength, we definitely can't claim we understand distant galaxies from one band alone. The Milky Way is the warning label. So here's where the tension increases. We finally have one galaxy we can map in 3D star by star, and even that one has hidden structure and hidden mass. If the nearest case already needs multiple wavelengths, careful dynamics, and uncertainty ranges, what happens when we step outside to other galaxies where we can't resolve individual stars? Next stop is the local group, and the first problem is simple. Even nearby, you're already dealing with mergers, streams, and dozens of small galaxies that can disappear unless you know exactly what to look for. If our galaxy is already hard to map from the inside, why should you trust anything we say about nearby galaxies outside it? Because the local group is close enough that we can still do detailed measurements, but far enough that we can compare whole galaxies cleanly. So what is the local group in plain terms? It's a gravitationally bound collection of galaxies. Bound means the galaxy's relative motions and the total mass are such that, overall, the group isn't just drifting apart with cosmic expansion. The local group is dominated by two big galaxies, the Milky Way and Andromeda. Everything else is mostly smaller galaxies, especially dwarfs. That matters because it tells you what typical really is. Most galaxies by number are not like the Milky Way. They're much smaller and fainter. The local group is your closest lab where you can study that full range, from big spirals down to tiny dwarfs. Now the obvious hop, Andromeda, also called M31. Why is Andromeda so important? Because it's the nearest large spiral galaxy, and it gives you an external view of a Milky Way-type system. You can measure its disk, bulge, and halo without the "we're inside it" problem. And Andromeda is not a clean, isolated object. Its halo shows structure, stellar streams, shells, and overdensities. Those are not decorative. They're evidence of past mergers. When a smaller galaxy falls into a larger one, tidal forces stretch it out, and its stars get smeared into long streams. Over time, those streams wrap and mix, but in nearby galaxies, you can still detect them as coherent structures. In Andromeda, those streams and halo features tell you it has eaten smaller galaxies in the past. That's not a theory based on vibes. It's based on observed star distributions, velocities, and metallicities that match a merger history. Now take the next step, Triangulum, M33. Why do we care about a smaller spiral when Andromeda is the main event? Because smaller spirals are more common, and they behave differently. Compared to massive spirals, a smaller spiral like M33 tends to have a higher gas fraction relative to its stellar mass. In simple terms, it has a larger share of its mass in usable gas compared to the amount already locked into stars. That often means star formation can be more active relative to its size, but also more sensitive to interactions and gas inflow. Smaller spirals are also key to testing how star formation scales with mass. When you compare gas content, star formation rate, and stellar mass across galaxies, you see patterns that become scaling relations. M33 helps anchor those patterns close enough that we can measure them carefully. Now here's the part that changes the whole every galaxy idea. Dwarf galaxies dominate the count. In the local group, there are many dwarf galaxies around the Milky Way and Andromeda, and more continue to be found as surveys improve. Most dwarfs are low luminosity, and many are low surface brightness, which means they're easy to miss even when they're nearby. This connects directly to the missing faint galaxies problem in galaxy counts. The issue is not that dwarfs don't exist, it's that detecting and cataloging them is hard. Some dwarfs have a small number of stars above the background, so you find them by looking for small statistical overdensities of stars, not by seeing a bright galaxy image. Others are tidally disrupted and spread out, making them even lower surface brightness. When you move from the local group to distant surveys, those kinds of galaxies are exactly what drop out first. That's one reason total galaxy estimates can jump when detection methods improve. Now here's the next question that forces the tension upward. Are these galaxies just sitting there, or are they on trajectories that will change everything? We can measure their motions. Proper motion is sideways motion across the sky. Radial velocity is motion toward or away from us. Combine those and you get 3D velocity information. With that, astronomers run simulations of future dynamics, but it's not blind guessing. It's initial conditions from data plus gravity. For the Milky Way and Andromeda, measurements show they are moving toward each other overall, and that makes a future interaction likely on cosmic timescales. The exact timing and details depend on the uncertainties in the measured velocities and the mass distribution, but the point is, we have enough data to model plausible futures with error ranges. That's how you turn what might happen into here are the outcomes consistent with the measurements. So the local group hop teaches you 3 things fast. Big spirals build by mergers, smaller spirals help test how gas and star formation scale with mass, and dwarfs dominate the count but are the easiest to miss. And the moment you track motions, the local group stops being a static neighborhood and becomes a system evolving in time. Now, the next step increases the pressure. Once you leave the local group, you enter crowded environments where galaxies don't evolve quietly. They get stripped, quenched, and reshaped by their surroundings. That's where galaxy evolution stops being a phrase and becomes a measurable environmental effect. If galaxies were isolated, would they even look the way they do? The answer shows up the moment you enter a cluster. A cluster is not just more galaxies in one place. It's a different physical environment that changes what galaxies are made of and how they evolve. Start with the Virgo Cluster, because it's the first major crowd in our neighborhood. It's the nearest large, rich galaxy cluster, and it's close enough that we can study individual galaxies in detail while still seeing the full cluster structure. What's the main observed difference between cluster galaxies and field galaxies, meaning galaxies out in lower density regions? In dense environments like Virgo, you see a higher fraction of ellipticals and lenticulars, and fewer classic gas-rich spirals compared to the field. You also see spirals in Virgo that look disturbed. Truncated gas disks, stripped tails, and altered star-forming regions. This is not subtle. The environment changes galaxy shapes, and especially gas content. And gas is the fuel for future star formation. Remove the gas, and the galaxy's future changes immediately. So what is actually doing the stripping? Here's the part people miss if they only think about gravity: intra-cluster gas. Clusters are filled with extremely hot, thin gas between galaxies. You don't see it in optical light because it's not glowing like a nebula. You see it in X-rays because gas at tens of millions of degrees emits strongly at X-ray energies. X-ray observations show that clusters have a huge reservoir of hot intra-cluster medium spread across the cluster volume. Now put a galaxy into that. The galaxy is moving fast through the cluster, often at hundreds to over 1,000 kilometers per second. When it plows through this hot gas, it experiences ram pressure. In normal language, it's like a wind that pushes on the galaxy's own gas. If the pressure is strong enough, it can strip the galaxy's cold gas out of the disk. You can literally observe this: galaxies with gas tails pointing away from their direction of motion, truncated star-forming disks where the outer gas has been removed, and in some cases, enhanced star formation on the leading edge where gas is compressed before it gets stripped. Ram pressure stripping is one of the cleanest environment changes galaxies mechanisms because it produces visible directional signatures and it connects directly to X-ray measured intra-cluster gas density. Now take the next step and connect it to the biggest population level effect: quenched galaxies. Quenched means their star formation rate has dropped to very low levels. In clusters, you see more red galaxies and more ellipticals. That color shift is not an aesthetic. Blue light comes from short-lived, massive young stars. If star formation stops, those stars die quickly on cosmic timescales, and the galaxy's light becomes dominated by older, redder stars. So clusters having more red galaxies means clusters have more galaxies where star formation formation has been shut down or strongly reduced, and that's measured directly. Surveys measure star formation rates using indicators like ultraviolet light, specific emission lines from ionized gas, and infrared emission from dust heated by new stars. In clusters, those indicators drop for a larger fraction of galaxies compared to the field. The environment is not just changing shapes, it is changing star formation histories. Now here's where your flight stops being just about counting light and starts about weighing invisible mass: gravitational lensing in clusters. A cluster has a large mass, most of it dark matter. That mass bends light from background galaxies. In the strongest cases, you get arcs, multiple images, or even ring-like structures around the mass concentration. That's strong lensing, and it tells you the mass distribution in the core. But even when there are no dramatic arcs, there is weak lensing, tiny statistical distortions in the shapes of many background galaxies. You can't see it by eye in one galaxy image, but across thousands or millions of galaxies, you measure a shear pattern, and from that, you reconstruct a projected mass map. This is key. Lensing measures mass without caring whether the mass is bright or dark. It's one of the cleanest ways to map dark matter in clusters, and it's why clusters are used as major tests for our understanding of structure formation. Now ask the final practical question for this section. Why do cluster catalogs matter for every galaxy? Because clusters are controlled test environments. They sit at known distances with many galaxies in one region, so you can test detection completeness under crowded conditions, test deblending performance, and compare galaxy properties across a shared distance and environment. Clusters also contain a wide range of galaxy types: gas-poor ellipticals, stripped spirals, dwarf populations, and galaxies actively interacting. That makes clusters a place where you can calibrate how environment affects galaxy evolution and how survey selection affects biosphere counts. And because clusters can lens background galaxies, cluster fields also help you detect faint, high-redshift galaxies that would otherwise be below the detection limit, which feeds back into the missing galaxies issue. So the nearby cluster lesson is blunt. Galaxies do not evolve in isolation, and a dense environment can remove gas, shut down star formation, and reshape populations. At the same time, clusters are one of our best tools for measuring dark matter through lensing and for testing survey completeness. Now the tension increases again. If environment changes galaxies this much, then you can't just count galaxies. You have to classify them fast and at scale. And once you start classifying, you run into a new problem. At high distance, the shapes blur and the colors shift, and mistakes become systematic. If you only get one quick look at a galaxy as you fly past in a survey, what can you learn from just its shape and its color? A lot. And also, enough to fool you if you don't track the limits. Start with the main observed classes, the ones surveys actually use. Spirals have disks with spiral arms and usually ongoing star formation. Ellipticals look smoother and more rounded with little obvious structure, and they're often dominated by older stars. Lenticulars are in between. They have a disc shape but don't show strong spiral arms and usually have less star formation. Irregulars don't fit cleanly into disc or spheroid categories. They look messy, often because they're small, interacting, or dominated by patchy star formation. And dwarfs are not a shape so much as a scale. Low mass, low luminosity systems that can be spiral, irregular, or spheroidal, but are often hard to classify because they're faint and low surface brightness. Important detail: surveys don't always label these by eye anymore. They measure structural parameters, how concentrated the light is, how asymmetric it is, how clumpy it is, whether the light profile looks like a disk or a bulge. And they assign classes using rules or trained models. That's why you can classify millions of galaxies instead of a few thousand. Now the next fast marker is color, and here's the key pattern. Galaxies split into two big groups in large data sets. This is the color bimodality, the blue cloud and the red sequence. Blue galaxies are usually forming stars now. They have lots of short-lived, massive, hot stars that emit strongly in blue and ultraviolet. Red galaxies are usually not forming many new stars. Their light is dominated by older, cooler stars. When you plot galaxy color versus brightness or color versus stellar mass, you see a broad blue population and a tighter red population. This is not a small effect. It shows up in huge surveys, and it's one of the main ways we talk about galaxy evolution at scale, how galaxies move from star forming to quenched populations. But color alone can trick you, so you link it back to observables. Blue usually means high star formation indicators, like UV emission and strong emission lines from ionized gas. Red usually means weak star formation indicators. And you always keep the caveat, dust can redden a galaxy even if it's forming stars, so infrared data is often needed to confirm what the color means. Now zoom into features that sound cosmetic but are actually physical: bars, rings, and spiral arm patterns. A bar is a stretched structure across the central region of a disk galaxy. It matters because it can drive gas flows. Observations show gas can be funneled inward along bars, and that can correlate with central star formation or feeding the central black hole. Rings can form where gas piles up at certain resonances in the disk, and rings often show star-forming regions that are easy to detect in ultraviolet, H-alpha emission, and infrared. Spiral arms are not just decoration either. They are regions where gas is compressed, making it easier for star formation to happen. You can see this directly. Spiral arms often light up with young star clusters, H-alpha emission, and dust lanes. So when surveys classify barred spiral versus unbarred spiral, they are tagging real differences in how gas moves and where stars form. Now push the route outward in redshift and you hit a problem that raises the stakes. Morphology changes with redshift. When you look at galaxies in the early universe, you often see more clumpy, irregular, disturbed-looking systems. Some of that is genuine evolution. Early galaxies had higher gas fractions, higher interaction and merger rates, and more turbulent star formation, so their structure was less settled. But some of it is observational. At high redshift, the galaxies are smaller on the sky, fainter, and you're limited by resolution and sensitivity. Details like thin disks and faint outer arms can drop below the detection threshold. A clean spiral can look like a few bright clumps if you can only detect the brightest star-forming regions. Also, the light you observe at a fixed telescope wavelength corresponds to different rest frame wavelengths at different redshifts. That means you might be comparing ultraviolet structure at high redshift to optical structure nearby, unless you correct for it. Surveys handle this by using multiple bands and by trying to compare similar rest frame wavelengths when they study morphology evolution. Now the blunt question: how reliable is classification when galaxies get faint and small? This is where you have to be honest about limits. At high redshift, many galaxies blur into a few pixels, noise increases, and blending becomes more frequent. Human visual classification becomes inconsistent, and even automated methods struggle. So large surveys use machine learning trained on labeled samples and simulations. They feed the model examples of spirals, ellipticals, mergers, clumpy systems, and they train it to predict classes from images and measured features. But this does not make classification correct by default. It introduces measurable error rates. Surveys test those error rates with validation sets, compare different classifiers, and publish confusion matrices or reliability metrics. In plain language, they quantify how often the model calls a spiral an elliptical, how often it misses bars, and how those mistakes depend on brightness and redshift. That matters because if your classifier is biased at high Z, you can invent evolution that is really just classification failure. So the fast takeaway is shape and color are powerful because they're available for huge numbers of galaxies, and they track real physical states like star formation and structure. But the farther you go, the more the measurements are affected by resolution, noise, dust, and wavelength shifts. The classification still works, but only if you treat it as a measurement with error bars, not as a label you can trust blindly. Now the tension increases again. Even if you classify galaxies perfectly, you still haven't answered the most important question for the whole mission. What keeps them alive as star factories or shuts them down? That means you have to follow the fuel, gas. And once you start measuring gas across cosmic time, you find out quickly that the simple story doesn't survive. If stars are being made all over the universe, why aren't galaxies converting all their gas into stars and burning out fast? The answer is in the fuel supply, how it's stored, and how we measure it. This section is about what you can actually observe that tells you whether a galaxy is building stars, running low on fuel, or getting shut down. Start with the biggest visible gas reservoir, neutral hydrogen, called HI. This is hydrogen gas where the electron is still attached, not ionized. The key observational tool is the 21 centimeter line. Neutral hydrogen can flip its internal state and emit radiophotons at a specific wavelength around 21 centimeters. It's weak per atom, but galaxies have huge amounts of HI, so over large regions you can map it. When radio telescopes scan a galaxy, they detect that line emission and build a velocity map too, because the line is Doppler shifted depending on whether the gas is moving toward or away from us. What does that imply? Two big things. First, many galaxies have HI disks that extend much farther than the visible starlight disk. The gas disk is often larger than you'd guess from optical images. Second, HI is a reservoir, not the final step. It tells you the galaxy has raw material available, but it does not automatically mean stars are forming efficiently right now. So what is the immediate fuel for star formation? Molecular gas, mainly molecular hydrogen, H2. Stars form in cold, dense molecular clouds. The problem is that cold H2 is hard to detect directly in typical galaxy conditions, so surveys use a tracer molecule, carbon monoxide, CO. CO emits at radio and millimeter wavelength in specific spectral lines, and those lines are much easier to detect. Astronomers observe CO emission and use a conversion factor to estimate the amount of H2. That conversion factor is not universal. It depends on metallicity and conditions, so it carries uncertainty. But CO is still the workhorse because it correlates strongly with star-forming regions. Where you see strong CO, you usually see signs of star formation. HI alpha emission, young clusters, and infrared emission from dust heated by new stars. So the picture becomes practical. HI tells you how much gas is available in a broad sense. CO tells you how much gas is in the dense phase that can actually form stars soon. Now the next question. How do you measure how fast a galaxy is forming stars? You can't watch individual stars being born in distant galaxies. You measure star formation rate, SFR, using observable proxies. Ultraviolet light traces young, massive stars because they're hot and bright in UV. If a galaxy is UV bright, it usually means it has recently formed massive stars in the last tens of millions of years. But dust is heavily affected by UV. Dust absorbs UV very efficiently, so a dusty, star-forming galaxy can look UV dim even when it's forming stars quickly. H-alpha emission is another major tracer. It comes from ionized hydrogen in HII regions around very young massive stars. Those stars don't live long, so H-alpha traces star formation on short timescales, roughly a few million years. It's strong and measurable, but dust can still reduce it, and at high redshift, the line shifts into infrared, so you need the right instruments. Infrared emission traces dust reprocessed star formation. Dust absorbs UV and optical light from young stars and re-emits that energy in the infrared. So a galaxy can be faint in UV and still be very bright in infrared if it's dusty and forming stars intensely. That's why good surveys combine UV, optical, and IR to estimate SFR more reliably. If you only use one band, you can be badly wrong for certain galaxy types. Now take those measurements and look for patterns in large datasets. Two scaling relations are key because they come straight out of observations, not just theory. First is the relation between star formation and gas surface density. In plain language, if you measure how much gas there is per unit area in a galaxy disk and compare it to how much star formation per unit area is happening, you find a strong trend. More gas density generally means more star formation activity. The scatter matters too. Different environments and galaxy types sit above or below the average strength, but the overall relationship is one of the clearest empirical links between fuel and output. Second is the star-forming main sequence. If you plot star formation rate versus stellar mass for star-forming galaxies, most of them lie along a relatively tight band. More massive star-forming galaxies tend to form more stars per unit time. That's a huge result because it says normal star formation is not random. It follows a predictable pattern across large galaxy samples, and that pattern evolves with redshift. Galaxies in the earlier universe, on average, formed stars more actively for their mass than similar mass galaxies today. That's not a story. It's a measured shift in the main sequence across cosmic time. Now the last part is where you push the tension up. Starbursts and quenching are not vague terms, they are measurable states. A starburst is when a galaxy's star formation rate is much higher than expected for its mass, meaning it sits well above the main sequence. Observationally, starbursts often show strong infrared emission, strong emission lines, and compact star-forming regions. Many starbursts are associated with mergers or strong interactions because those events can compress gas and drive it inward, raising gas density and triggering rapid star formation. You can see the connection by looking at disturbed morphologies, close pairs, tidal features, and comparing their SFR indicators to matched non-interacting galaxies. Quenching is the opposite. A galaxy's star formation rate drops far below the main sequence for its mass. Observationally, you see weak UV and H-alpha, low infrared emission tied to star formation, and often less cold gas. In clusters, quenching can be driven by gas stripping and environmental effects. In massive galaxies, quenching can also correlate with central bulges, hot halos, and active black holes. The key point is you can measure it. Galaxies move off the star-forming main sequence, their colors shift to the red sequence, and their gas tracers decline or change distribution. So the fuel story is direct. HI maps the broad reservoir, CO maps the immediate star-forming gas, UV, H-alpha, and IR measure the star formation output, and scaling relations show consistent patterns across massive datasets. Starbursts and quenching are extreme states that show up clearly in those same measurements. Now the pressure rises again. Even if you know a galaxy's fuel and current star formation, you still haven't answered what it has been through. To get that, you need ages and chemistry. You need spectra, and you need to read them like forensic evidence, not like pretty rainbow plots. If two galaxies look the same shape and the same color, how can one be older than the other? You can't answer that from an image alone. You need spectra. A spectrum is what you get when you spread a galaxy's light into its wavelengths and measure how much light arrives at each wavelength. That's where ages and chemistry show up as measurable features, not guesses. So first, how do spectra give you ages? Realistically, you usually can't date a galaxy by pointing at one star. For most galaxies, you're seeing blended light from billions of stars. What you can do is estimate the mix of stellar ages statistically. Two parts matter: the overall shape of the spectrum and the absorption features. The shape tells you how blue or red the combined starlight is, which is sensitive to the fraction of young hot stars versus older, cooler stars. Absorption features are narrow dips where atoms and stellar atmospheres absorb specific wavelengths. Different types of stars produce different patterns. When a galaxy has a significant young population, you tend to see different strengths in certain absorption features compared to a galaxy dominated by older stars. In practice, astronomers fit models called stellar population synthesis models. These models combine the spectra of stars of different ages and chemical compositions to reproduce the observed galaxy spectrum. The output is not, this galaxy is exactly 6.2 billion years old. It's, this galaxy's light is best explained by this mixture of ages, with uncertainties. That's why the honest phrasing is, ages statistically, not ages perfectly. Now the next question, what does metallicity mean and how is it actually observed? In astronomy, metals means any element heavier than helium. So metallicity is the abundance of elements heavier than helium in a galaxy's gas and stars. It's measured from spectral lines. In gas, you use nebular emission lines, lines produced by ionized gas in star-forming regions. Ratios of lines from oxygen, nitrogen, hydrogen, and other elements change depending on temperature, density, and chemical abundance. Astronomers use calibrated methods to convert those observed line ratios into metallicity estimates. In stars, metallicity is measured from absorption lines in the combined starlight, again by fitting models. Either way, it's an observed quantity derived from spectral strengths and ratios, and it comes with systematic uncertainties because calibration methods differ. But the key is, metallicity is not a label you assign. It's a measurement tied to spectral data. Now take the next step. Gradients. Many spiral galaxies show metallicity gradients across their disks. In plain terms, the inner parts of spirals often have higher metallicity than the outer parts. You measure this by sampling H2 regions, or stellar populations at different radii and comparing their line ratios or absorption features. Why does that matter? Because it supports inside-out growth. If a disk forms stars over long periods, the inner region typically forms stars earlier and more intensely, enriching the gas with heavy elements faster. The outer disk builds up later and stays more metal-poor. This isn't just a story. The gradient is measurable, and it changes with galaxy mass, star formation history, and interactions. Mergers and strong gas inflows can flatten gradients by mixing gas. Outflows can also alter gradients by removing enriched gas. So, metallicity gradients are a way to test how a galaxy has processed and moved its gas over time. Now, the next hard anchor: globular clusters. Why do they matter so much? Because they are fossils you can measure cleanly in nearby galaxies. Globular clusters are dense, gravitationally bound clusters of old stars. Many are very old, often among the oldest stellar systems in a galaxy. You can measure their ages and metallicities from their integrated spectra and colors. And in the Milky Way, you can do even better by resolving individual stars. In other nearby galaxies, you can count globular clusters, map where they are, and measure their metallicity distribution. That distribution is useful because it tracks early assembly history. Different groups of globular clusters can indicate different formation episodes. Some formed early in the main galaxy, some may have been accreted when the galaxy merged with smaller systems. So, globular clusters are not decoration around the galaxy. They are a measurable record of how the galaxy was built. Now, push the route out to high redshift, and reality hits hard. These detailed stellar population fits become much harder. The main limit is faintness. High redshift galaxies are faint, and long exposures are expensive. Often, you don't get a clean, high signal-to-noise spectrum with lots of absorption features. Instead, you may detect strong emission lines from ionized gas and measure broadband colors from multiple filters. Those still give constraints. Emission lines can tell you about current star formation, gas metallicity estimates, and sometimes dust content. Broadband colors can constrain age, dust, and metallicity combinations, but there are degeneracies, meaning different mixtures can produce similar colors. That's why the honest phrasing is ages statistically, not ages perfectly. Now, the next question: what does metallicity mean, and how is it actually observed? In astronomy, metals means any element heavier than helium. So, metallicity is the abundance of elements heavier than helium in a galaxy's gas and stars. It's measured from spectral lines. In gas, you use nebular emission lines, lines produced by ionized gas in star-forming regions. Ratios of lines from oxygen, nitrogen, hydrogen, and other elements change depending on temperature, density, and chemical abundance. Astronomers use calibrated methods to convert those observed line ratios into metallicity estimates. In stars, metallicity is measured from absorption lines in the combined starlight, again by fitting models. Either way, it's an observed quantity, derived from line strength and ratios, and it comes with systematic uncertainties because calibration methods differ. But the key is, metallicity is not a label you assign. It's a measurement tied to spectral data. Now, take the next step: gradients. Many spiral galaxies show metallicity gradients across their disks. In plain terms, the inner parts of spirals often have higher metallicity than the outer parts. You measure this by sampling H2 regions or stellar populations at different radii and comparing their line ratios or absorption features. Why does that matter? Because it supports inside-out growth. If a disk forms stars over long periods, the inner region typically forms stars earlier and more intensely, enriching the gas with heavy elements faster. The outer disk builds up later and stays more metal-poor. This isn't just a story. The gradient is measurable, and it changes with galaxy mass, star formation history, and interactions. Mergers and strong gas inflows can flatten gradients by mixing gas. Outflows can also alter gradients by removing enriched gas. So metallicity gradients are a way to test how a galaxy has processed and moved its gas over time. Now, the next hard anchor, globular clusters. Why do they matter so much? Because they are fossils you can measure cleanly in nearby galaxies. Globular clusters are dense, gravitationally bound clusters of old stars. Many are very old, often among the oldest stellar systems in a galaxy. You can measure their ages and metallicities from their integrated spectra and colors, and in the Milky Way you can do even better by resolving individual stars. In nearby other galaxies, you can count globular clusters, map where they are, and measure their metallicity distribution. That distribution is useful because it tracks early assembly history. Different groups of globular clusters can indicate different formation episodes. Some formed early in the main galaxy, some may have been accreted when the galaxy merged with smaller systems. So globular clusters are not decoration around the galaxy. They are a measurable record of how the galaxy was built. Now push the route out to high redshift, and reality hits hard. These detailed stellar population fits become much harder. The main limit is faintness. High redshift galaxies are faint, and long exposures are expensive. Often, you don't get a clean, high signal-to-noise spectrum with lots of absorption features. Instead, you may detect strong emission lines from ionized gas and measure broadband colors from multiple filters. Those still give constraints. Emission lines can tell you about current star formation, gas metallicity estimates, and sometimes dust content. Broadband colors can constrain age, dust, metallicity combinations, but there are degeneracies, meaning different mixtures can produce similar colors. That's why spectroscopy is still the gold standard when possible, especially for confirming redshifts and identifying physical conditions. But for many high-Z galaxies, the best you can do is combine emission line information with multi-band photometry and accept wider uncertainties. So the takeaway is direct. Spectra let you estimate age mixtures and metallicity. Gradients show how disks build and mix. Globular clusters preserve early assembly information. And at high redshift, the measurements get harder, so the constraints shift toward emission lines and broadband colors with larger error bars. Now here's the tension jump. Once you can read spectra, you start seeing extremely bright, compact sources that don't fit normal starlight. They show broad lines, strong X-rays, and sometimes radio jets. Those are active galactic nuclei, and they can outshine their entire host galaxies. If your flight is built on photons, these objects can dominate the signal and distort your counts unless you treat them correctly. If you're trying to count galaxies fairly, what do you do with objects that can outshine an entire galaxy from a region smaller than our solar system? That's the AGN problem. AGN, active galactic nuclei, are not a galaxy type in the normal sense. They're a phase where the center is actively feeding a supermassive black hole, and the light from that feeding can dominate what you see. So what is an AGN observationally? In images, many AGN look like a bright, point-like nucleus sitting in a galaxy. It can look like a star placed at the center, except it doesn't behave like a star when you measure its spectrum. In spectra, AGN show strong emission lines. Some AGN show broad emission lines, meaning the lines are widened because the gas is moving extremely fast around the central source. Others show narrow lines, meaning the gas we see is moving slower or we're viewing a different region. Many AGN are strong X-ray sources because gas very close to a black hole gets heated to extreme temperatures. Some AGN also produce radio jets, collimated outflows that emit strongly at radio wavelength and can extend far beyond the galaxy itself. So the observational definition is not, "we saw a black hole." The definition is a package of measurable signals, a bright nucleus, specific line patterns, high energy emission, and sometimes jets. Now the next question is the mechanism, but keep it tied to what we measure. What powers that output? Accretion. Gas falls towards the black hole and forms an accretion disk. As gas spirals inward, it heats up and radiates. That radiation is what we measure. You don't need equations to understand the constraint. There is a maximum steady brightness a black hole can sustain for a given mass before radiation pressure pushes infalling gas away. That's the Eddington idea. In plain language, if you see a certain luminosity and you assume it's powered by accretion, you can estimate the minimum black hole mass needed to produce that luminosity without blowing its fuel supply apart. That's why luminosity gives you mass scale constraints. And we don't just use total brightness, we use spectra and variability. Spectra show the continuum shape and emission line strengths, which tell you about the energy distribution and gas conditions. Variability is also a big deal. AGN can vary on timescales from days to years. That tells you the emitting region is compact because a large region can't change brightness coherently fast. So between luminosity, spectral features, and variability, you can constrain what the central engine must be like, even when you cannot spatially resolve it. Now the most extreme case, quasars. Why do quasars matter for this fly through the universe story? Because quasars are bright enough to be detected at very high redshift when normal galaxies are much harder to detect. A quasar can outshine its host galaxy by a huge factor. That means quasars act as markers of the early universe. If you find a very high redshift quasar, you know a massive black hole already existed when the universe was young. That creates a real scientific pressure. How did black holes grow that fast? But for our route, the practical point is simpler. Quasars are visible across extreme distances, so they are powerful probes and also major selection effects. They can dominate samples if you're not careful, because they are overrepresented in flux-limited surveys. Quasars also help with another job, distance and environment probing. Their spectra contain absorption features from gas clouds along the line of sight, which can be used to study the intergalactic medium between us and the quasar. So a quasar is not just a bright point. It's a backlight that reveals what's in between galaxies and around them. That matters when your goal is every galaxy, because the space between galaxies is part of the structure you're flying through too. Now step to a key empirical result: black hole galaxy correlations. How do we know supermassive black holes are connected to their host galaxies in a systematic way? Observationally, we find correlations between black hole mass and properties of the galaxy bulge, like bulge stellar mass and velocity dispersion. This wasn't assumed, it was measured by combining dynamical black hole mass estimates in nearby galaxies, where you can measure stellar or gas motions close to the center, with black hole mass estimates in AGN using reverberation mapping and other methods. Then you compare those masses to host galaxy bulge measurements from imaging and spectroscopy. The correlation has scatter and exceptions, but it's real enough to be one of the main constraints on galaxy evolution models. It implies black hole growth and bulge growth are linked, either through shared gas supply, feedback, or coevolution over time. The important point for a survey-based flight is that you can't treat black holes as rare side events. They are connected to how galaxies build their central structures. Now here's the part that can quietly ruin a census if you ignore it: duty cycles and selection bias. We only see AGN when they are on, meaning actively accreting and radiating strongly. Most black holes spend a lot of time in low activity states, where they are hard to detect as AGN. So if you make a catalog of AGN and call that the black hole population, you're wrong by definition. Surveys have to correct for the fraction of time black holes are active, the luminosity threshold of detection, and the fact that dust and orientation can hide AGN in certain wavelengths. That's why multi-wavelength selection is used. X-rays can find AGN hidden in optical, infrared can find dust-obscured AGN, and radio can find jet-dominated AGN. Even then, the sample is incomplete, and papers model that incompleteness explicitly. So the takeaway is direct. AGN are identified by measurable signatures. Their luminosity and variability constrain a compact accretion engine. Quasars reach high redshift and act as early universe markers. Black hole mass correlates with host bulge properties, and AGN samples require duty cycle corrections because activity is intermittent and selection is biased. Now the tension increases again. If AGN and galaxies are sitting inside massive dark matter halos, then a lot of what you think is a galaxy map is actually just the visible layer of something you can't see directly. The next section has to deal with the invisible mass that shapes the route, dark matter. If most of the mass in the universe doesn't emit light, then what are you actually flying through when you fly through galaxies? You're flying through a structure built mostly out of invisible mass. Galaxies are the lit-up parts. The underlying framework is dark matter, and we know it's there because it changes motions and bends light in ways normal matter can't explain. Start with the classic measurement, galaxy rotation curves. This is the cleanest place to see the problem. In a spiral galaxy, you can measure how fast gas and stars orbit the center at different radii. You do it with Doppler shifts. Spectral lines shift depending on whether the material is moving toward or away from us. Map the shifts across the disk and you get the rotation speed as a function of distance from the center. If almost all the mass were in the bright stars and gas you can see, you would expect orbital speeds to drop as you go farther out, because the gravitational pull would weaken with distance once you're past most of the mass. But what you observe in many spirals is that the outer rotation stays high instead of dropping as expected. The simplest interpretation is that there is extra mass extending far beyond the visible disk. That's the dark matter halo. And this isn't a one galaxy story. Rotation curves are measured in many spirals with different sizes and brightness, and the outer speeds stay high pattern is common. The details vary, but the basic need for extra mass is consistent. This is why dark matter is treated as an observational requirement, not a speculative add-on. The data forces you to add mass where there is little light. Now move to galaxies where rotation curves aren't the main tool, ellipticals and dwarfs. Elliptical galaxies don't have a cold, rotating disk in the same way spirals do, so you often can't map a clean rotation curve. Instead, you measure velocity dispersion, how fast stars move in random directions. You do that by measuring how broadened the absorption lines are in the galaxy spectrum. Broader lines mean stars have a wider spread of velocities. That spread tells you how deep the gravitational potential is. When you compare the implied total mass to the amount of starlight, you often get a mass-to-light ratio that's too high to be explained by normal stars alone, especially in the outer parts. Dwarf galaxies are even more extreme. Many dwarfs have very little light, but their stars can still have surprisingly high velocity dispersions. That implies the system is held together by a lot of mass compared to its light. In some dwarfs, the mass-to-light ratio is so high that most of the mass must be non-luminous. Dwarfs are important because they push the dark matter question into a regime where stars are clearly not the main mass component. Now, the next measurement is the most direct in one sense because it doesn't care about how stars move. Gravitational lensing. Mass bends light. If you measure the distortions of background galaxies caused by foreground mass, you can map the projected mass distribution. Weak lensing is the key for large-scale mapping. You measure tiny systematic shape distortions, shear, across millions of background galaxies. Individual galaxies have random shapes, so you need huge samples, but the average distortion pattern reveals the mass distribution along the line of sight. This mass includes dark matter automatically because lensing responds to total gravity, not to light. That's why weak lensing is used to map dark matter in galaxy halos, groups, clusters, and across the cosmic web. Now scale up to clusters and do a mass budget. Clusters contain galaxies, hot intra-cluster gas, and dark matter. The hot gas is observed in X-rays and can be very massive, sometimes more massive than all the stars in the cluster galaxies combined. But even when you add up all the normal matter you can see, stars plus hot gas, it still doesn't match the total mass implied by lensing and by the motions of galaxies within the cluster. Lensing and dynamics consistently show that most of the cluster's mass is not in stars. This is one of the strongest pieces of evidence because clusters are large systems where multiple independent methods agree. Galaxy velocities, X-ray gas properties, and lensing all point to a dominant unseen mass component. Now, here's how this changes your flight map in a practical way. If you only map visible galaxies, you get a picture of where light is. That's useful, but it's not the full structure. Galaxies trace filaments and clusters, so a galaxy map outlines the cosmic web, but lensing maps show the mass scaffolding more directly. The filaments and nodes exist as mass concentrations first, and galaxies form and live inside those halos. So the most accurate route through the large-scale universe is not follow the brightest galaxies. It's follow the mass distribution, because that's what determines where galaxies form, how they cluster, and how they evolve in different environments. This is also where a lot of survey interpretation becomes strict. If you see a region with fewer galaxies, is it truly underdense, or did your survey miss faint galaxies there? Lensing can help answer that because it responds to total mass. If lensing shows low mass, it's a real void. If lensing shows mass but you see fewer galaxies than expected, that's telling you about bias, detection limits, or galaxy formation efficiency in that environment. So the core message is direct. Rotation curves, velocity dispersions, and lensing all require extra mass beyond what emits light. Cluster mass budgets confirm it at large scale. And for your mission, this means the visible galaxy tour is really a tour of the bright tracers sitting on an invisible framework. Now the tension jumps again. If mass is doing the shaping and light is just tracing it, then the best way to reach the faintest galaxies isn't always to build a bigger telescope. Sometimes you use mass itself as a tool, because gravity can magnify light. That's gravitational lensing, and it's how you push galaxy counts into territory you shouldn't be able to reach. If a galaxy is too faint for your telescope, how can you still detect it without changing the telescope at all? You let gravity do the work. Gravitational lensing is not a special imaging trick. It's a direct consequence of mass bending spacetime, which bends light paths. In surveys, lensing is both a tool and a source of confusion, depending on if you model it correctly. Start with strong lensing because it's the easiest to see. Observationally, strong lensing shows up as multiple images of the same background source, stretched arcs, or near-complete rings called Einstein rings. You see it most clearly in two situations: massive galaxy clusters lensing many background galaxies, and single massive galaxies lensing a background galaxy or quasar. In cluster fields, you can get dramatic arcs because the mass is huge and concentrated. In galaxy-galaxy lensing, the effect can produce smaller arcs or partial rings around the foreground galaxy. The key point is observational. You can identify strong lensing because the shapes and symmetries are distinctive, and you can confirm it when the multiple images have matching spectra and redshifts. Now, here's why lensing matters for the every galaxy goal: magnification. Lensing can make a background galaxy appear brighter and larger on the sky than it would without the foreground mass. That means galaxies that would normally fall below the flux limit of your survey can become detectable. In plain terms, without lensing, they're too faint to register. With lensing, they cross the detection threshold. This is a major way surveys push galaxy counts deeper, especially at high redshift. It's also how we study very small, early galaxies that would otherwise be out of reach. The magnification is not uniform. It depends on the exact alignment and the mass distribution of the lens. But when you target known strong lensing cluster fields, you increase the chance of finding highly magnified background galaxies. There's a catch, and it matters for honesty. Lensing changes more than brightness. It also distorts area and volume. If you're using lensed fields to count galaxies, you can't just count detected sources and call it the true number density. You have to correct for the magnification and the fact that the observed patch corresponds to an effective source plane area. Lensing can boost your sensitivity, but it also complicates the conversion from what we saw to how many exist. That leads directly to lens models and uncertainties. To use lensing properly, you need a model of the lens mass distribution to estimate magnification maps. For strong lensing, models are constrained by the positions and shapes of arcs and multiple images. Different modeling approaches, different assumptions about how smooth the dark matter distribution is, how much mass is in individual galaxy clusters, and how substructure is handled, can produce different magnification estimates. This matters because inferred properties of background galaxies, like intrinsic brightness and size, depends on the magnification. If the magnification is off, the galaxy is mischaracterized. That's why good surveys publish ensembles of lens models and uncertainties, not a single the answer. They also compare model families and show how results change. In plain language, lensing gives you a boost, but you pay for it with model dependence, and the uncertainty must be carried through the analysis. Now switch to weak lensing, because that's how lensing becomes a large-scale mapping tool. Weak lensing is not about dramatic arcs. It's about tiny distortions in galaxy shapes caused by foreground mass. Any single galaxy has an unknown intrinsic shape, so you can't tell if one is lensed by looking at it alone. But if you measure shapes for millions of galaxies, the random orientations average out, and the remaining coherent pattern reveals the shear field. From that, you infer a projected mass map. Weak lensing is used to map dark matter around galaxies statistically, to map clusters, and to measure the growth of structure across cosmic time. It's a core method because it responds to total mass, including dark matter, and because it doesn't require assumptions about how stars and gas move. Now, the practical point that keeps lensing tied to the rest of your mission. Lensing is also a consistency check. In clusters, you can estimate mass in several independent ways. You can use lensing to infer mass from light bending. You can use dynamics to infer mass from galaxy velocities and velocity dispersions. You can use X-ray observations of hot gas to infer mass from the gas temperature and distribution, assuming the gas is roughly in equilibrium with the cluster's gravity. These methods have different systematics. If they agree within uncertainties, it increases confidence. If they disagree, it points to issues like non-equilibrium gas, complex geometry, substructure, or biases in selection and modeling. So lensing isn't just a zoom lens. It's a separate measurement channel that tests whether your mass estimates are internally consistent. So the lensing section boils down to this. Strong lensing produces multiple images and arcs that can be used to magnify and study faint high-redshift galaxies. Lens models are necessary and introduce uncertainty. Weak lensing uses statistical shape distortions to map mass, and comparing lensing mass to dynamical and X-ray mass helps catch systematics. Now the tension increases again. If mass is shaping everything and lensing shows you the hidden framework, the next question is obvious and dangerous. What does the large-scale structure actually look like in 3D, and how do galaxies sit inside it? That's the cosmic web, and once you map it, every galaxy stops being a list and becomes a network. What does a universe look like when you stop thinking in galaxies and start thinking in structure? Because once you map enough galaxies, you don't see random dots. You see a pattern, filaments, nodes, and voids. Here's the practical version. Galaxy redshift surveys take positions on the sky and add redshift so you get a 3D map. In that map, galaxies line up in long, dense strands called filaments. Where several filaments intersect, you get nodes, and those nodes are where big groups and clusters tend to sit. Between filaments, you get voids, huge regions with far fewer galaxies. This isn't a drawing style. It's what the 3D data looks like when you plot millions of galaxies in co-moving coordinates. Now ask the next question. Is this web just where galaxies are, or does the web itself have measurable motion? Recently, we got a concrete observation that pushes this from a static map to a dynamics. Astronomers reported a rotating filament detected with Meerkat radio observations, a filament about 50 million light-years long, containing close to 300 galaxies, with large-scale rotation reported around 396,000 kilometers per hour. That matters because it's not just galaxies spinning internally, it's evidence of rotation on a filament scale, which is the kind of thing simulations have suggested could happen, but direct detection is hard because the signal is subtle and you need enough galaxies and good velocity data. Now the tension point. If mass is shaping everything and lensing shows you the hidden framework, the next question is obvious and dangerous. What does the large-scale structure actually look like in 3D, and how do galaxies sit inside it? That's the cosmic web, and once you map it, every galaxy stops being a list and becomes a network. So how do you put a ruler on a map that's billions of light years across? You use baryon acoustic oscillations, BAO. Keep it practical. In the early universe, pressure waves traveled through the hot plasma. When the universe cooled enough for atoms to form, those waves stopped traveling freely, and they left a preferred separation scale imprinted in the matter distribution. Today, when you measure how galaxies are clustered, that imprint shows up in a bump in the two-point correlation function, meaning there's a slight excess of galaxy pairs separated by that scale in co-moving distance. And why do cosmologists care so much? Because BAO gives you a standard ruler. You measure how big that scale appears across the sky and along the line of sight at different redshifts, and that constrains the expansion history. It's not based on one rare object, it's based on statistics across huge samples, which is exactly what you need for a census-style mission. Now tighten the focus. What happens to galaxies inside different parts of the web? Start with voids, because voids are the cleanest environment test. In voids, galaxies have fewer close neighbors and fewer strong interactions. That tends to reduce merger and harassment rates compared to filament and cluster environments. And because interactions and stripping are less common, void galaxies can often retain more cold gas relative to their size, which affects star formation. Observational studies look at gas fractions and molecular to atomic gas ratios in void galaxies and compare them to galaxies in denser environments, and they find measurable environmental differences that depend on stellar mass and gas phase. On the star formation side, the key idea is not void galaxies always form more stars. The honest statement is, environment shifts the distributions. Some analyses find that void galaxies can sustain higher star formation activity and lower metallicities than filament galaxies at similar masses, consistent with more isolation and continued gas accretion, while denser environments show more processing and enrichment. The details vary by sample and mass range, so you treat it as a measured trend with scatter, not a rule with no exceptions. Now flip to filaments and nodes. Filaments are where galaxies are more likely to experience moderate interactions. Gas flows along structure and pre-processing before they ever enter a rich cluster. Nodes and clusters push that to the extreme, stripping, quenching, and higher fractions of red galaxies. So when you say every galaxy, you can't act like there's one average galaxy experience. The environment changes gas content, star formation, and morphology, and the environment itself is part of the map. So here's what your flight plan has to do if it's going to be truthful. You don't just move outward by distance, you also hop by environment. You explicitly do void, filament, cluster. And you repeat that across redshift shells, because the same galaxy mass can behave differently depending on where it lives in the web. And if you ignore that, your universal story becomes a biased sample. Now the next pressure question. If the cosmic web is real structure, and if background light is faint, and if your measurements depend on clean calibration, what's the floor under every observation? Because there is always background light under your signal, and it sets hard limits on what galaxies you can detect at all. What's the one thing every galaxy photo has in common, no matter where you point the telescope? There's always background light under it. If you don't control that background, your galaxy count becomes a counting mistake. Start with the biggest background of all, the cosmic microwave background, the CMB. This is real measured radiation coming from all directions. Its temperature is about 2.7 Kelvin, which is just a way of saying it's cold microwave light. It's not coming from stars. It's the oldest light we can see directly, released when the universe cooled enough for electrons to stick to nuclei and make neutral atoms. Before that, light couldn't travel freely because it kept scattering. After that, the universe became transparent and that light started free streaming. So the CMB is the earliest surface we can see. And it's not perfectly smooth. It has tiny temperature differences across the sky, anisotropies, at the level of a few parts in 100,000. That small pattern is a big deal because it is the cleanest picture we have of the early universe's density structure. So here's the next question. Why should a microwave background matter for a mission about galaxies? Because the CMB tells you the starting conditions for everything that formed later. Those tiny anisotropies correspond to tiny density differences, slightly denser regions and slightly less dense regions. Gravity amplifies those differences over time. The denser regions grow into the structures where galaxies form: halos, filaments, clusters. When we do galaxy surveys and measure how galaxies cluster, we are measuring the later time result of growth from those early fluctuations. That's why CMB data isn't just cosmology trivia, it sets the baseline, how much structure you should get, on what scales, and how it should evolve. If your galaxy clustering measurements don't connect back to the CMB constraints, something is wrong, either with your model of cosmic growth or with your measurement systematics. Now tighten it. If the CMB is the earliest light, what's the background made by all galaxies combined? That's the extragalactic background light, the EBL. In plain terms, it's the integrated light from all galaxies over cosmic time across wavelengths from ultraviolet through optical into infrared, including the part that got absorbed by dust and re-emitted at longer wavelength. You can estimate parts of it directly by summing light from resolved galaxies in deep surveys. But you also have to handle the fact that not every galaxy is resolved, and diffuse components exist. Another way we constrain EBL is indirectly. Very high-energy gamma rays traveling through intergalactic space can get absorbed by interacting with EBL photons. So the amount of absorption seen in distant gamma ray sources limits the EBL intensity. The key point for this mission is simple. Even empty sky contains real background light from real cosmic sources. When you try to detect the faintest galaxies, you are working against that floor. So what stops you from just subtracting the background and moving on? Foregrounds. This is where the counting gets dangerous. The biggest foreground in many optical and infrared observations is zodiacal light, sunlight scattered by dust in our own solar system. It can be smooth and bright enough to dominate the background in certain bands. Then there's the Milky Way itself, diffuse dust emissions, scattered starlight, and complicated structure that varies across the sky. When you point near the galactic plane, you're not doing deep universe work. You're fighting foregrounds and confusion from dense star fields. Even when you point to clean fields, Milky Way cirrus, diffuse dust structures, can add low-level brightness fluctuations that look like faint galaxies if you're careless. And it's not just astrophysical foregrounds. Instruments have backgrounds too. Detector noise, thermal emission from the telescope and infrared, stray light, and small calibration drifts that create gradients across the image. The big failure mode is this. When you push to extreme faintness, the difference between real low surface brightness galaxy and imperfect background subtraction can be small. That's why background modeling is not a boring technical step. It decides which galaxies exist in your catalog and which ones vanish. Now ask the sharpest question. If backgrounds and foregrounds are this serious, how do surveys keep galaxy counts trustworthy? Calibration. This is where small errors become big science mistakes. Photometric calibration sets the conversion from detector counts to real flux. If your 0 point is off by a small amount, your magnitudes shift, and that shift's number counts, because galaxy counts rise steeply toward the faint end. A tiny systematic shift can change how many galaxies appear above your detection threshold. Flat field calibration corrects pixel-to-pixel sensitivity differences. If it's imperfect, you can create artificial patterns that mimic diffuse structure. Point spread function modeling matters because it affects how you measure shapes and how you deblend overlapping sources. Bad PSF handling can merge galaxies or split them incorrectly, changing the catalog. Background subtraction itself must be consistent across the field. If you subtract too aggressively, you erase low surface brightness galaxies. If you subtract too weakly, you inflate fluxes and create false detections. This connects directly to luminosity functions, which are used to estimate total galaxy numbers. A luminosity function depends on accurate fluxes, accurate completeness estimates, and accurate redshift bins. Small photometric errors can move galaxies between brightness bins and even between redshift estimates if you're using photometric redshifts. That changes the inferred number density, the faint end slope, and the total integrated galaxy count. This is why serious surveys publish completeness functions, calibration uncertainties, and systematic error budgets. It's not decoration. It's the difference between trillions of galaxies being a measured inference versus a broken pipeline output. So here's where the tension spikes. The floor under your observations is real, and it's made of ancient light. integrated galaxy light, and local foregrounds. The faintest galaxies live right at the edge where calibration errors and background modeling can erase them or invent them. Now, the next question is unavoidable. If the CMB is the earliest light we see directly, and everything after it depends on photons escaping through gas and dust, then where do galaxies first become visible at all? Because there's a time when galaxies exist, but their light can't travel freely, and getting past that boundary is the next big wall in this flight. How far back can you go before a galaxy stops being a normal object and becomes a fragile signal that can vanish if you measure one thing wrong? This is that zone, first galaxies and reionization. Let's anchor this with something confirmed, not a maybe. JWST has spectroscopically confirmed JADE's GSZ140 at redshift about 14.32, meaning we see it as it was less than 300 million years after the Big Bang. Spectroscopically confirmed is the key phrase. It means they didn't just find the red object in images and hope. They took a spectrum, identified real spectral features, and measured how far those features shifted in wavelength. That's how you lock in an extreme distance instead of guessing from colors. Now, the next question, what wall are we hitting physically? Reionization. After the universe cooled enough for electrons to join nuclei, the gas between galaxies was mostly neutral hydrogen. Neutral hydrogen blocks ultraviolet light very efficiently at the Lyman series, especially around the Lyman alpha wavelength. During reionization, ultraviolet radiation from the first stars, galaxies, and black holes ionized that hydrogen, turning it into plasma. Once the neutral fraction drops enough, UV light can travel much farther and the universe becomes much more transparent. So what do we actually observe that tells us reionization is happening? Two main channels. First, Lyman alpha visibility in galaxies. Lyman alpha is a UV emission line that can be strong in star-forming galaxies, but it's also extremely easy for neutral hydrogen to scatter. If the intergalactic medium is more neutral, Lyman alpha photons get scattered out of the line of sight, and the line gets suppressed or disappears. If the region around the galaxy is more ionized, more Lyman alpha can escape and you can detect it. JWST has now reported very high redshift spectroscopy where Lyman alpha is detected even at Z equals 13, which is a big clue that ionized regions can exist surprisingly early. Second, absorption signatures from neutral hydrogen in bright background sources. The classic example is the Gunn-Peterson trough in high redshift quasar spectra. Flux drops sharply blueward of the redshifted Lyman alpha line because neutral hydrogen along the path absorbs and scatters it. The practical point is simple. Neutral hydrogen absorption is so strong that even a small neutral fraction can create a dramatic trough. So these spectra are sensitive tests of how neutral the intergalactic medium is at different times. Now here's what JWST has made impossible to ignore. Some early galaxies look brighter, and in some cases more extended than many pre-JWST expectations. In the Nature spectroscopy work, JADE's GSZ140 is described as luminous and clearly extended compared with JWST's point spread function, with emission detected out to about 1 kiloparsec, roughly 3,000 light-years. And broader summaries of JWST results underline the same pressure point: more bright galaxies early on than people were ready for. So how do you turn a few headline objects into a statement about the whole era? Statistics. The core tool is the UV luminosity function versus redshift. In normal language, for a given time slice, you measure how many galaxies exist at each UV brightness. Then you correct for what you miss, faint objects, low surface brightness, and blending, and you integrate that distribution to estimate the total UV light produced per unit volume. Reionization models then connect that UV output to an ionizing photon budget by adding the real-world messy parts, like how much UV is absorbed by dust, what fraction of ionizing photons escape the galaxy, and how clumpy the intergalactic gas is. Now, the last problem before you claim you've reached the edge: selection effects. Most extreme redshift candidates are first found using dropout selection, also called the Lyman break technique. You look for a sharp drop in flux between filters because light shortward of Lyman alpha gets absorbed, so the source disappears in bluer bands and appears in redder bands. It's powerful, but it has predictable contaminants. One contaminant is cool dwarf stars in our own Milky Way, M, L, and T dwarfs. Their colors can mimic a high redshift dropout, especially when the object is faint and unresolved. Deep searches also deal with low redshift galaxies that have strong breaks or heavy dust reddening, plus plain old blending, where two separate objects overlap and the combined colors fake one extreme redshift source. That's why teams run strict filtering, do cross-checks across extra bands, and publish purity estimates, because candidate is not the same as confirmed. So the rule that keeps the frontier real is simple. Photometry finds candidates. Spectroscopy confirms reality. Photometry is fast and can push to huge samples, but it can be fooled by dust and by local stars. Spectroscopy is slower and harder, but when it locks onto a line or a set of features, the redshift becomes solid and the object becomes a real anchor for the timeline. And that leads straight to the next tension question. If galaxies exist less than 300 million years after the Big Bang and some are already bright, what does their chemistry look like? Because the moment you detect heavier elements that early, you've proven stars already lived and died fast enough to enrich the gas. That's the next section. If you claim you've reached an early galaxy, how do you prove it already had generations of stars, not just raw hydrogen? You look for heavy elements, because heavy elements don't come from the Big Bang in large amounts. They come from stars living, burning, and dying. So how do we detect elements in a galaxy in a way that's actually measurable? Two main ways: emission lines and absorption lines. Emission lines come from gas. If gas is heated by young stars or an active nucleus, atoms like oxygen, nitrogen, carbon, and hydrogen emit light at specific wavelengths. You take a spectrum and those show up as bright spikes at known positions. Absorption lines come from starlight passing through stellar atmospheres, where certain atoms absorb specific wavelengths, creating dips in the spectrum. Both are real data. You're not inferring oxygen from vibes. You're measuring line patterns and strengths and matching them to physics. Now here's the next question. What does metallicity actually mean when astronomers say it? It means the abundance of elements heavier than helium. That includes oxygen, carbon, nitrogen, iron, and everything else built in stars. In gas, metallicity is usually estimated from ratios of emission lines in H2I regions. In stars, it's estimated from absorption features in the combined starlight. Either way, it's a number with uncertainty and calibration choices, but it's grounded in spectral measurements. So, what's the big observed trend across cosmic time? Metallicity increases on average. Nearby massive galaxies tend to have higher metallicity than distant early galaxies because they've had more time to form stars and recycle material. Reviews of galaxy chemical evolution summarize this as a consistent pattern: higher redshift, lower average metallicity at fixed mass, with scattered depending on gas inflows, outflows, and star formation history. And when you hear people say dex, here's the simple translation. 1 dex means a factor of 10. So if something is 0.3 dex higher, it's about a factor of 2 higher. That's the scale of many real metallicity comparisons. Not tiny, not infinite, but noticeable. Now the pressure point: rapid enrichment in the early universe. If you find oxygen or carbon in a galaxy that early, it means stars already formed, evolved, and enriched the gas fast. JWST has pushed this into the uncomfortable zone. For example, JADE's results report carbon enrichment in a galaxy seen about 350 million years after the Big Bang, with unusually high carbon to oxygen implications that point to enrichment from very metal-poor stars early on. And for the extreme frontier objects, we're seeing direct evidence that some systems are chemically more mature than older first galaxies should be pristine expectations. ALMA reported oxygen in the very distant confirmed galaxy JADE's GS-Z14, and the summary point is clear. Oxygen that early implies rapid chemical evolution. There's also work reporting bright oxygen lines and metallicities that are not near zero even a few 100 million years after the Big Bang, reinforcing the same conclusion. Early galaxies can enrich quickly. Does that mean every early galaxy is metal-rich? No. Some high redshift galaxies show weak or absent metal lines consistent with low metallicity. The honest statement is there is diversity early on. Some systems look surprisingly enriched, others look more primitive. That diversity is part of the measurement, not a problem to hide. So, how do you avoid overinterpreting one flashy detection? You compare populations. Recent JWST-based studies look at line ratios like nitrogen to oxygen and report systematic offsets at high redshift compared to local trends at the level of a few tenths of a dex in some regimes. That's important because it's not just we saw one weird galaxy. It's evidence that enrichment pathways and gas conditions can differ in early galaxies, likely tied to bursty star formation and rapid inflows and outflows. Now the next question: are metals spread evenly inside a galaxy? No. Metals have gradients and they get mixed. In many nearby spiral galaxies, inner regions are more metal-rich than outer regions. That's one of the key observational supports for inside-out growth. The center forms stars earlier and more intensely, enriching faster, while the outskirts build up later. But gradients are not fixed. Gas inflows can bring in lower metallicity material and dilute central regions. Outflows driven by supernovae or AGN can remove enriched gas. Mergers and strong interactions can stir gas and flatten gradients by mixing different regions together. You can literally see this in data. The slope of metallicity with radius varies by galaxy type, mass, and interaction history. And outer disks often show gradient changes that hint at gas flows and mixing processes. So why does any of this matter for the Fly Through Every Galaxy mission? Because chemistry is a timestamp and a process marker. If you detect low metallicity and certain line patterns, you're probably looking at a system that hasn't recycled much material yet. If you detect higher metallicity and certain enrichment signatures, you're looking at a system that already went through earlier star formation and feedback. Chemistry helps separate genuinely early stage from already processed, even when two galaxies have similar brightness. It also tells you what your selection is doing. If your survey preferentially detects brighter, more chemically mature galaxies at high redshift, you may be missing the faint, more primitive population that matters for the true count and for reionization. Now here's the tension. Jump into the next section. If metals appear early, something had to assemble galaxies fast, feed them gas, trigger star formation, and mix and redistribute that enriched material. So what's doing the heavy lifting? Quiet growth or violent growth? Because the next thing you see everywhere in deep imaging is not smooth evolution, it's interaction, distortion, and merging signatures. If galaxies grow over time, is it mostly calm growth or is it violent growth? The data says both happen, but mergers are a major piece. And the good part is, mergers leave signatures you can actually observe. Start with the most direct evidence: tidal tails, streams, and disturbed morphologies. In nearby galaxies, you can see long tidal tails, extended ribbons of stars and gas pulled out by gravitational forces during an interaction. You can see shells and loops in galaxy halos, which are leftover structures from smaller galaxies being torn apart and absorbed. You can see warped disks, asymmetric arms, double nuclei, and messy outer light profiles. These are not subtle if you have deep imaging. They're direct signatures that gravity has recently rearranged the galaxy. In the local group, we see streams around the Milky Way and Andromeda. In external galaxies, deep images reveal tidal structures that normal shallow images miss. The key point is, you don't need to believe in mergers, you can see the debris. Now here's the next tension. For distant galaxies where tidal details are harder to detect, how do you measure merger activity at scale? Close pairs. Surveys look for galaxies that are near each other on the sky within some projected separation, and also near each other in redshift, meaning their line-of-sight velocities differ by a limited amount. That combination filters out chance alignments. If two galaxies are close in both projected distance and velocity, there's a significant chance they're gravitationally interacting and may merge within a timescale that simulations can estimate. So pair counts become a merger rate estimator. You measure the fraction of galaxies in close pairs as a function of redshift and mass, correct for selection effects, and convert that into an inferred merger frequency. It's not perfect, but it's measurable and it's widely used because it scales to huge catalogs. Now the next tension. Even if mergers happen, how much do they really matter for building galaxy mass? You have to separate two growth channels. One is in situ star formation. The galaxy forms new stars from its own gas. The other is ex situ growth. The galaxy gains stars that formed elsewhere, brought in by mergers and accretion of smaller galaxies. Observationally, you estimate in situ growth by measuring star formation rates over time and integrating them to get how much stellar mass could have formed inside the galaxy. You estimate ex situ growth by looking at how stellar mass functions evolve, by studying stellar halos and streams in nearby galaxies, and by comparing galaxy structural growth to what star formation alone would produce. The conclusion depends on mass. Lower mass galaxies are often dominated by in situ star formation over much of their history, while very massive galaxies can gain a large fraction of their stars through mergers, especially later times. You don't have to memorize exact percentages to keep it honest. The important point is that both channels are required and their relative importance changes with galaxy mass and with cosmic time. Now make it concrete with something you can measure during an interaction: merger-triggered starbursts and AGN. When galaxies interact, gas can lose angular momentum and flow inward. That raises gas density in central regions, and higher density tends to increase star formation. Observationally, interacting systems often show elevated star formation indicators compared to isolated galaxies of similar mass. A major signature is enhanced infrared luminosity, because dusty starbursts emit strongly in IR as dust absorbs UV or optical light from young stars and re-emits it as thermal radiance. Many luminous infrared galaxies are mergers or strongly interacting systems. At the same time, the inflow that feeds star formation can feed the central black hole, turning on an AGN. So you often see increased nuclear activity in certain interaction stages. This is not a universal rule. Many mergers don't produce an extreme starburst, and many AGN are triggered by other processes. But the correlation exists in populations. Interaction increases the probability of starbursts and AGN activity above baseline. Now for the part that prevents this from turning into a story: simulations but checked against observations. The honest use of simulations is not the simulation said it happened, so it happened. The honest use is you simulate galaxy populations with gravity, gas physics, star formation prescriptions, and feedback. Then you ask measurable questions. Do the simulations reproduce the observed close pair fraction as a function of redshift and mass? Do they reproduce the observed distribution of galaxy sizes and how sizes evolve? Do they reproduce the fraction of disturbed morphologies at different depths and resolutions? Do they reproduce the observed starburst fraction and the typical star formation enhancement in interacting pairs? When simulations disagree, that's not a small detail. It means your merger timescales, feedback strength, gas inflow behavior, or selection modeling is off. So simulations are useful only when they're forced to match survey statistics and when they predict new measurable patterns that can be tested. So the merger section is simple in data terms. You can see tidal debris nearby, you can count close pairs to estimate merger rates in large surveys, you can compare in situ star formation growth to ex situ accretion growth. You can measure starburst and AGN enhancements in interacting systems, and you can test simulations by whether they reproduce these statistics. Now the tension step. If mergers, star formation, and the growth of structure all depend on distance and time, then your whole route depends on how accurately you can measure distances across the universe. And that's where the expansion measurement problem hits. Because if your distance scale is off, your entire map shifts. If your whole route is built on redshift, here's the problem you can't dodge. How do you turn z into real distance without quietly inventing the scale? If the distances are off, the entire flight path is off. Start with the most direct method we have, parallax. Parallax is geometry. As Earth moves around the sun, a nearby star shifts a tiny bit against the background of more distant stars. Measure that shift angle and you get distance. No model of the star needed. But parallax only reaches so far. Past a certain range, the shift is too small to measure cleanly. So parallax becomes the foundation for calibration, not the tool for mapping other galaxies. So how do you jump from local geometry to other galaxies? You use standard candles. A standard candle is an object whose true brightness can be inferred from a measurable property, so brightness becomes a distance tool. Cepheid variable stars are the classic rung. Cepheids pulse with a stable period, and that period is linked to their true luminosity. You measure the period from the light curve, infer how luminous a star really is, then compare that to how bright it looks from Earth to get distance. That's why Cepheids matter so much. They connect nearby and geometric to outside the Milky Way. But what if the galaxy is too far for you to detect Cepheids one by one? Then you climb to a brighter rung, Type 1a supernovae. These explosions can be bright enough to see across billions of light years. They're not perfectly identical, but their light curves have predictable shapes that let astronomers standardize the peak luminosity. The latter procedure is concrete. Use parallax to calibrate Cepheids. Use Cepheids to calibrate distances to galaxies that host Type 1a supernovae, then use Type 1a supernovae to measure distances to much farther galaxies. Here's the tension point. It's called the ladder because each rung depends on the rung below. If the Cepheid calibration shifts, your supernova distances shift. If those shift, your inferred expansion rate shifts. That's why teams fight systematics like dust reddening, crowding where stars overlap in images, and tiny photometric calibration offsets. When you later build galaxy counts versus distance, those small biases can turn into huge differences in totals. So is there a distance method that doesn't rely on the local ladder? Yes, BAO, Baryon Acoustic Oscillations. BAO is a standard ruler, not a standard candle. In the early universe, pressure waves set a preferred separation scale in the matter distribution. Today, when you measure how galaxies cluster, that old scale shows up as a bump in the statistics at a characteristic co-moving separation, often summarized as about 150 megaparsecs. You measure how that ruler appears across the sky and along the line of sight at different redshifts, and you constrain the expansion history from the clustering data itself. Now the next hard truth. BAO is independent in method with different systematics than the latter, but it still sits inside a cosmological model. You're translating angles and redshifts into distances in an expanding universe, so parameters still matter. The value is that BAO cross-checks the latter using totally different data and totally different failure modes. Now push harder. Is there a one-step method that avoids Cepheids and also avoids using the BAO sound horizon as its anchor? Strong lens time delays. When a foreground galaxy lenses a background quasar, you can get multiple images of the same quasar. Quasars vary in brightness over time. Because the light paths differ in length and also pass through different gravitational potentials, the same brightness change arrives at each image at a different time. You measure those time delays, model the lens mass distribution, and that gives you a distance scale that is strongly sensitive to the expansion rate. Now the question people always ask, and you can't answer it softly. Why do Hubble constant numbers vary? Because the major methods don't perfectly agree. Early universe fits to CMB data under the standard model land around 67 kilometers per second per megaparsec, while local distance ladder results land around the low 70s, around 73. That mismatch is the Hubble tension. It's a measurement tension because the stated uncertainties are small enough that the gap is hard to explain as random noise. Time delay lensing sits in the same fight. Some analyses land closer to the local ladder, but lensing results depend on lens mass modeling, mass along the line of sight, and the lens galaxy's internal kinematics. That's why modern time delay work is obsessed with uncertainty budgets, and with adding extra constraints like stellar velocity measurements, so the result is not a fragile number that changes when you tweak one assumption. So what changes in your flight map if those parameters shift? The structure doesn't disappear. Filaments, clusters, and voids still exist. Redshift still orders your route in time. What changes is the precise conversion from redshift to co-moving distance and look-back time. If the expansion rate today is higher, a given redshift corresponds to a slightly different distance scale than if it's lower. That changes inferred volumes and number densities, and it shifts the precise placement of boundaries in your redshift shells. Your map doesn't break, but the rulers you use to label it move, and that matters when you claim totals. So here's the clean takeaway. Your route is only as solid as your distance anchors. The latter uses geometry and standard candles. BAO uses a standard ruler in clustering. Time delay lensing uses gravity and time delays. They don't fully agree yet, and that disagreement means there's either a remaining systematic error somewhere or the standard model is missing something. Now the tension jumps. If the distance scale itself is still under pressure, what happens when we enter the era where surveys stop being a few deep fields and become billions of sources, where tiny completeness errors can swing the total galaxy count by enormous amounts? If you're still thinking this mission is a few deep images and a lot of hype, stop. The only way to get anywhere close to every galaxy is to move from small samples to a census, where the measurements are standardized, repeatable, and brutally honest about what gets missed. So what's the modern strategy? Deep and wide at the same time. Deep fields tell you what exists at the faint end. Wide fields tell you how galaxies are distributed, how rare objects show up, and how environment changes everything. JWST is now doing this with Cosmos Web in the Cosmos field. It mapped about 0.54 square degrees with JWST's near-infrared camera, and about 0.2 square degrees with the mid-infrared instrument. Out of that, teams built the Cosmos 2025 catalog, with measurements for nearly 700,000 galaxies. And here's the key point you're supposed to feel. This kind of dataset spans roughly 13 billion years of cosmic history in one coordinated map. That's the big survey era. You stop telling stories about single galaxies and you start measuring how the whole population changes across time. Now ask the next question. Why obsess over one field of sky like Cosmos instead of picking any random dark patch? Because field choice controls your errors before you even start. You want low foreground dust, a low and stable infrared background, and not too many bright foreground stars that create scattered light and bury faint detections. The Cosmos field was chosen to have among the lowest and most uniform 100-micron infrared background levels for a big equatorial field, specifically to reduce foreground contamination and make faint galaxy detection easier. Then there's the practical reason that makes Cosmos a powerhouse: coverage. Cosmos already has deep multi-wavelength observations and lots of existing spectroscopy from earlier campaigns, including deep radio imaging over the same field with strong overlap to other bands. So when JWST adds infrared depth, you can connect one galaxy to many kinds of measurements: stars, dust, gas, and black hole activity. That's how a census turns into physics instead of just a lot of dots. Now the next tension point. Images are not the map. Catalogs are the map. Survey pipelines take raw images, model the background, detect sources, separate overlapping sources as best they can, measure fluxes in each filter, estimate shapes and sizes, and attach quality flags. Then they compute derived quantities like stellar mass, star formation rate, and redshift estimates, and they store uncertainties for each one. Cosmos 2025 is explicitly described as a catalog that includes photometry, structural measurements, redshifts, and physical parameters for that huge galaxy sample. Now, the make or break step for a census: completeness functions. This is not optional. Detection probability drops with apparent brightness, but it also drops with size and surface brightness. A compact faint galaxy can be detected while a larger diffuse galaxy with the same total light can vanish into the background. Blending hides faint galaxies next to bright ones. Background subtraction can erase low surface brightness outcurves if it's too aggressive. So surveys measure completeness with injection and recovery tests. They insert fake galaxies with different magnitudes, sizes, and profiles into the images, run the same pipeline, and measure what fraction gets recovered. That recovery rate becomes a correction, and those corrections feed directly into galaxy totals and luminosity functions. Now, ask the next question that raises the stakes. How do you place hundreds of thousands of galaxies in 3D without taking spectra for all of them? Photometric redshifts, trained and calibrated. You measure fluxes across many filters, you get a color pattern, and you estimate redshift from that pattern. Cosmos 2025 includes photometric redshifts as a core product. But photo-Z values are fuzzier than spectroscopy, and they fail in predictable ways. Dust can make a nearby galaxy look like a much more distant one. Strong emission lines can distort broadband colors, and at the faint limit, the noise alone can scatter you into the wrong redshift bin. So how do surveys control that? Training and cross-checks. You take spectroscopic subsamples, galaxies with redshifts measured from real spectral lines, and you use them to calibrate the photometric redshift system. Then you measure how the errors depend on brightness, color, and galaxy type. The end product isn't "this is the true redshift." It's "this is the probability distribution for redshift," because that's what you need when you're doing clustering and population statistics. And here's the part that can quietly break your 3D map. Errors don't stay local. If photo-Z has a small systematic bias, inferred distances shift, volumes shift, number densities shift, and clustering signals blur. Filaments look weaker, voids look less empty, and environment trends can get flattened or faked. That's why series releases include quality flags, uncertainty distributions, and recommended cuts, because downstream work needs to know what's solid and what's not. Now, lock in the data volume reality. Cosmos 2025 alone is around 800,000 galaxies. At that scale, fly through every galaxy is powered by statistical summaries, redshift shells, mass bins, color splits, morphology fractions, and environment slices. You do not visit 800,000 objects. You measure populations, quantify selection effects, correct for incompleteness, and then you check that your conclusions survive when you vary assumptions inside the allowed uncertainties. So here's the pressure point. Once surveys reach this scale, the main risk isn't that we don't have enough galaxies. The risk is that small systematic errors in calibration, completeness, or redshift estimation get multiplied into big wrong conclusions. And if your goal is every galaxy, that's the moment where the story either becomes real science or it becomes a confident mistake. Next section closes the loop. What you can say truthfully about every galaxy, what you can't, and where the frontier marker is right now. If you say we're flying through every galaxy, what can you say that's actually true and what's just not possible? First, the hard limit. We will not resolve every galaxy as an individual object with current tech, not even close. The faintest galaxies are below detection thresholds. Some are too low in surface brightness. Some are blended into brighter neighbors. And at high redshift, the signal is weak and stretched into infrared. So the honest method is inference. You measure what you can detect, and then you correct for what you miss using completeness functions and luminosity functions. That's how the hundreds of billions turns into maybe trillions, without pretending we personally saw them all. This is also why totals always come with ranges. If someone gives you one exact number with no uncertainty, they're skipping the hard part. So then, what's the right way to build the census? Here's the clean split. Deep fields and wide fields do different jobs, and you need both. Deep fields go after the faint end. They tell you what the small, dim galaxies look like, how many appear when you push lower in brightness, and how galaxy properties change in the early universe when you can actually detect them. They are the only way to measure the faint population directly. Wide surveys go after volume. They map large-scale structure, find rare objects that deep fields may miss because the area is tiny, and let you measure environment effects, voids versus filaments versus clusters, without being dominated by cosmic variance. Wide surveys are also where you get strong statistics for clustering, BAO, and population splits by mass and color. If you only do deep, you don't know if your tiny patch is representative. If you only do wide, you miss the galaxies that dominate by number. Now, here's the next question that makes every galaxy slippery. What do you even count as a galaxy? Because different catalogs will not match, and it's not always because one is wrong. Do you count ultra-diffuse galaxies that are huge but very low surface brightness? Some surveys miss them unless the pipeline is tuned for diffuse detection. Do you count tidal dwarfs, objects formed from stripped material during interactions that may not be long-lived or may not be clearly bound? Do you count barely bound systems with very low star counts where the line between galaxy and star cluster gets blurry? Even in the nearby universe, there are borderline objects. In distant surveys, the border expands because you can't resolve stars, and you're classifying by light profiles and colors. So galaxy count depends on detection rules and definitions. That's not a loophole. That's a real part of observational astronomy. So if you're going to present the flight honestly, how should the route look? Not as a checklist, not as a "we visited them all." It should be a structured sequence through bins, where each bin is a measurable slice of the universe. You start local because that's where we can do 3D and dynamics, the Milky Way in detail, then local group members, then nearby groups and clusters like Virgo, where environment physics is obvious. Then you step outward in redshift shells. You're not traveling to a point. You're sampling populations at a given look-back time and measuring distributions, luminosity functions, mass functions, color splits, AGN fractions, gas tracers when possible. And finally, you hit the earliest confirmed galaxies where you stop pretending you have a full census and you start talking about confirmed anchors plus statistical limits. So here's the last question that decides where the route ends today. What is the current frontier marker? As of 2024, the big confirmed anchor was JWST Z14-0, spectroscopically confirmed at redshift 14.32, less than 300 million years after the Big Bang. But the edge moved again in 2025. MOMZ14 was reported as spectroscopically confirmed at redshift 14.44, corresponding to about 280 million years after the Big Bang. Based on JWST near SPEC/prism spectroscopy with multiple rest UV emission lines and a sharp Lyman break. And this is the rule that matters. The edge of the route is not set by the reddest-looking candidate in an image. It's set by spectroscopy. Candidates can go higher on photometric redshift, but the frontier marker only moves when spectroscopy confirms a new record. That's why the edge keeps shifting. Better infrared data finds candidates, but real confirmation requires lines and breaks measured in spectra. So here's the honest close. We can't literally visit every galaxy, and we can't individually resolve most of them. What we can do is build a measured census using deep fields, wide surveys, and corrections that are published and testable. We can map where galaxies sit in the cosmic web, how they change with time, and how many we infer exist below detection limits. And the end of the flight is not a philosophical boundary. It's simply the highest confirmed redshift we can defend with spectroscopy today, and it will move again when the next spectrum makes it real. Explained like that, every galaxy stops being a claim and becomes a method. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.